I have a zoom picture here. I have no control.
There might be a delay.
Oh, there is a delay. Yeah, all right. So very simply, polynomial systems, you have a set of unknowns and you have a set of polynomials. And an example, a simple example is given there in two equations, two unknowns. And so if it's linear, it's easy to solve. And if the higher power, it's harder to solve. You need specific techniques for that. And as these systems grow larger and larger, then it's harder and harder to solve. So one technique tries to reduce all these systems to one equation. One equation, one unknown is really easy to solve. We know how to do that. But if you have 30 equations, 30 unknowns, and each of them has degree 2, when you go to single equation, now you're in the 60s, degree becomes unstable. And even if you can solve it, it's not usable. So HC avoids doing that. And that's really the punchline. I just gave it to you. So these happen in a diverse set of applications. Polynomial systems are everywhere. Mechanical engineers use it. I have colleagues at Brown who use it for stress strain analysis of the material. Happen in a great number of applications. And the one that we're particularly interested in is in computer vision. And these happen in multi-view geometry a lot in particular. Why multi-view geometry gives you polynomial systems? Anybody? What's the core factor that you get polynomial systems from these multi-view applications? Because you have a projection from 3D to 2D, and those gives you equations relating the 3D point to 2D point. And those, a series of them make up polynomials. And I'll show you examples of that. That's why in all the multi-view geometry problems, you end up with polynomial systems. So the classic one is the relative pose estimation for two views. It's been solved. Nister had algorithms and others. And so let's just walk through a couple of these so we have something concrete to talk about, even though everyone knows how to solve it. So here, you have a bunch of points, image points, that are in correspondence with a bunch of other points in another image. So those are the little gammas. The little gammas, gamma 1 in correspondence to gamma 1 bar, and gamma 2 and gamma 2 bar. And once you have those correspondences, the fact that they arise from a common 3D point, and the common 3D point is big gammas, gives you now a constraint. Gamma in 3D space is rho times little gamma. Little gamma is a vector in 3D, which just has constraint to the image plane by having the focal plane. So depth times that point, that's a constraint, and that is the constraint in the other coordinate system. Now you bring them together by relative pose, that's the constraint. The constraint is you take the coordinate in one, rotate and translate, you get the other one, and these are the basic equations, right? So now if I put them together, so I only have the observables, the little gamma I bar that I observe in an image. Rho is the depth. I don't know it. So this is one unknown. This is another unknown. R and T are unknown. I don't know them. There's metric ambiguity. I can scale these up by tenfold and make the depth tenfold. Nothing will change. So we can't really solve for that. So you might think that R and T have 6 unknowns, 3 for R and 3 for T, but they have only 5 because T, I don't know the scale of it, so that becomes a unit vector. So now I have 5 unknowns from the pose. That's the desirable. But I have latent variables as well that are not known. One depth, the depth in first frame, the depth in the second frame. You got n of them, you get 2n unknowns. Okay, so what are the set of unknowns? Relative pose, that's 5. And if you have n points, there are 2n unknowns there. How many equations I have? I have 3 equations, a vector equation, 3 equations. So I have 3n equations. Okay, so if I have, what's the minimum number that can solve it? You solve it, you find out n is equal to 5. With 5, I now give a 15 by 15 system. 15 unknowns, 15 equations. Does anyone solve this 15 by 15? No. Why? Because you can get rid of depth. In each equation, you can get rid of depth. You basically get rid of R and, I'm sorry, get rid of the depth. You dot product with E3, you get this one, you put in the other one, you get these, you use two equations to solve the depth, and you're left with what's known as the epipolar equation. The epipolar equation gives you E, which is TXR, relating, it's a 3 by 3 matrix, but there are no 9 unknowns. There are only still 5 unknowns because there are constraints on E, but it's one equation. So one equation per pair of unknowns, and now we have a better system. We have a 5 by 5 system. Can I solve that? Well, I have to now put in this constraint because E as a product of R and T does not have 9 unknowns, has 5. So I need to borrow these constraints to solve it. So how is it typically done? You use the 5 points to constraint E, lives in a 4-dimensional space now because it has 9 unknowns. And then you solve these cubic equations. By the way, these are cubic because E gives you cubic. And so you solve these now. You basically have 9 cubic polynomials, and you reduce them to a single 10th degree polynomial, high degree, but it's okay. And you solve it. And this is how it's been done. You can also use a resultant method, and that has been done. Thank you so much. Thank you, I appreciate it. And so now that's standard. It's been done for many years. So that works. What's the point of discussing this particular classic problem? Is we didn't have to go through hoops. Right here, when you write down the equation, you say, oh, it's a 15 by 15 system. Use homotopy continuation to solve it. You don't have to go through ingenuity of eliminating variables and reducing it to a 10th order polynomial because I know how to solve 10th order polynomial. I also know how to solve 15 by 15. That's the point of this tutorial. Okay, so that's one example. Another classic example is absolute pose estimation. How many points you need? You need 3 points. 3 points in space, 3 points in your image. You can move it around until the 3 points match. So these are the points in 3D space. These are points in the image. I need them to match. These are the equations. R and T is the absolute pose. Now, how many unknowns I have? I no longer have 5. I have 6. There's 6 unknowns because there's no metric ambiguity. So now I have 6 unknowns. And wait a second, but I also brought in the 3 depth variables. Okay, so I have 6 from here and 3 from here. That's 9. But hey, that's good because I also have three vector equations, each of them 3. So now I have a 9 by 9 system. How is it typically done? Does anyone solve the 9 by 9? No. What do? You eliminate something. What do you eliminate? One option is eliminate R and T from the previous one. So for example, you subtract these equations, you eliminate T. You subtract these 2 equations, you eliminate T. Now you have 2 vectors equations in R and the 3 depths, 6 by 6. Do you solve that? No. You also get rid of R. Isolate R and multiply it by RT, get rid of R, and you end up with 3 equations. These are the 3 equations. 3 equations, 3 unknowns. Okay, now that's better. Now that's better. So people try to always reduce the system to something that's more manageable. But hey, now I've got higher powers, higher degree. Okay, so you reduce it you eliminate 2 of the depths, you end up with an 8 degree, which is really 8 degree with even terms, so that's like a quartic. And alternatively, you can eliminate depths and T, and you solve for R. And So basically now it can be used. So what's the point here? The point is that these systems we know how to solve. We know how to do them in the way I just described. But what I want to bring you back here is the minute you wrote down these equations and you had 9x9 polynomial system, just solve it using homotopy continuation right there. You don't need to be a genius about it and go through tricks to reduce it. Okay, so these were the two classic problems that didn't need any, we don't need them. We already have solution for them. But when you go to more complicated problems, let's say trifocal relative pose estimation, and you either do it from point correspondences or points with lines at the points. And here's, in this particular case, we have points that have some kind of a line through them, so some kind of tangent direction is available to us. And we can do it with three correspondences, two of them having lines. What are the unknowns here? The unknowns is the relative pose of one with respect to two and one with respect to three. One of them there is metric ambiguity, so one variable goes out. So instead of 6 and 6, we have 6 and 5, 11 unknowns there. We also have depths that are at each of the three correspondences. So 3 unknowns per image, so that's 9. And we have a total so far of 20 unknowns. The point correspondences give us equations here totaling 18. And then when we throw the direction on, and I won't go through this calculation, we introduce additional variables, but also additional equations. The bottom line is you end up with 30 equations and 30 unknowns. And now you say, how do I solve that? And so this is, now you got trouble. Now this is where HC comes in and can help you solve these. Can also do trifocal relative pose estimation. You say, if I have unknown focal length, I can just do it with point correspondences, but instead of 3, now I need to have 4. And now with 4, we have 11 unknown pose, 1 unknown for low focal length, and 12 depths, 3 for each of the 4 points. I have 24 unknowns. I have 24 equations. Now I have a 24 by 24 polynomial system. Again, as the number goes up, as it becomes larger, then it puts constraint on the using classical techniques. And that's where HC is going to shine. But in order for HC, for homotopy continuation to be workable, you have to know how to solve it. Okay, another problem. So whenever you have cameras that are together in a rig, they're fixed, you can consider them as a generalized camera. And the advantage is now you know that you fix the scale for the two of them. You have a wider field of view because they're over larger space. And to do this with now 3-view generalized system, now you have 12 degrees of freedom. And there are two kinds of scenarios that come up. You either do it with 4 points or with 6 lines. And when we consider this, then again, we're left with polynomial systems that are 12 polynomial equations in 12 unknowns, or 6 in 6 unknowns. Okay, and one more problem is multi-view triangulation. This has been known to be helpful if you have 2 or 3 views. As you add the number of views, the degree becomes more complicated. So while the additional view surprisingly helps, you need to have many of them, but it's harder to solve. And so we can eliminate that possibility, something we have done, and make it grow less rapidly. But at the end, what happens here? Large polynomial system, large number of unknowns. And so in all of these, the lesson is not to reduce that to a single polynomial. That's not what we want to do. Because when you do that, with especially with the high number of unknowns, the degree shoots to the roof and becomes unstable. And so we want to solve it in its native form in the large polynomial domain. Okay, so I'm now passing the baton on to Hongi, who will discuss the classic ways of solving these methods and where we will have problems with that. Please.
All right. Hello, everyone. I'm Hong Yifan, and this is a tour of solving polynomial systems in computer vision. And the goal of this talk, sorry, I cannot see my. Okay. The goal of this talk is I'll give a brief overview of the existing techniques in solving polynomial system. There's no need to have any algebraic background, algebraic geometry background. And we will give a simple analysis of their pros and cons and their application scenarios. And before we start going through all these existing techniques, let's first see what's the requirements of an ideal polynomial solver. What do we want in a polynomial solver? The first one thing we want is that it should be stable and accurate. So accurate, I don't need to introduce quite a lot. We need to have an accurate root, and it needs to be stable, and the solution needs to be stable for different coefficients for both integer and floating numbers, and for both small numbers and really large numbers. And another thing we want from an ideal solver is it should be fast. And since we have a bunch of real-time applications, we need to solve polynomial systems in ransacs a bunch of times, so we need it to be fast enough. Okay, and several more properties we want in an ideal polynomial solver includes it needs to be easy to access. Like no one wants to read all these yellow books of mathematics, right? And it should be a solver that anyone can use. You don't need to know a lot in algebraic geometry. And you don't need to manually doing some research, doing some transformation on your problem. It needs to be easy to access. And another feature is it should be easy to initialize. Like for a system that has thousands of solutions, you need to have a low initialization effort. And third one, and the last feature we want in an ideal solver is it should be scalable. One should be able to solve quite large number of unknowns and equations. It may open the door to more problems and more applications. So,
can you share the screen again? It came off Zoom.
Okay. Oh, right. So, all right. Okay. All right. And then we have this big chart that we have all these nice features that we want in a solver, and we will see if each technique fits this chart or not. The first method we want to see is the Newton's method. Everybody knows how to write it, how to implement it. It's really simple. I won't go deep quite into it. It has its own issue. It relies heavily on the initial guess for one problem, you need to know at least one initial guess, then you can apply this Newton method, and you can apply, you can reach to one solution. And if we met the systems like what I listed here, for example, the trifocal relative pose, without knowing the focal lengths and the trifocal relative pose, they have thousands of, hundreds of, and thousands of solutions. If we know only one initial solution, we cannot reach all the solutions we want, and we cannot guarantee it's the solution, it's the actual solution we want. So it only fits for some kind of solution reinforcement refinement application or some incremental solvers. So what do we have in this chart? It's Newton's method is quite stable and quite accurate, and it's really fast, and it's easy to access. Everyone knows how to implement it, but it's not easy to initialize. And we can apply Newton's method in a quite big problem, so it's scalable. And another alternative method is some general solvers. The idea of general solvers is basically the variable elimination. It's the extension of the traditional Gauss-Jordan elimination to multivariable polynomials. So on the left-hand side, you can see it's the idea of Gauss-Jordan elimination. You have one linear system, and you manipulate among different equations, and you triangulate it. Finally, you have a you have the solution of this system at the very last row of this matrix. The same thing can apply on the multivariable polynomials. For example, we have on the right-hand side, we have a matrix of coefficients. Each coefficient corresponds to one monomials, one term on the top. We do some manipulations on the rows. For example, we multiply x on the first row, subtracts to the second row, and blah blah blah. Do all these kind of complicated operations. We might end up with a single variable polynomial showing on the right-hand side. So ideally, this general solvers, this variable elimination idea is supposed to solve any polynomial equations, but it's not trivial. There are two well-known methods. One is called resultant. The other is called Grobner basis. So let's check them one by one. So the resultant method, the resultant is defined as a polynomial expression that of their coefficients that is equal to 0 if and only if the polynomial has common roots. So as an example, we revisit this quite classic 5 points algorithm. We have this 5 points algorithm settings, and we can transfer it to a polynomial system with 10 equations and 3 unknowns. And we can rewrite there's 10 equations and 3 unknowns to a matrix representation on the right that we hide the variable z into the coefficient matrix and end up with this x itself is the monomial, is a set of monomials of 2 variables. And this linear system has solution if and only if the determinant of its coefficient matrix is 0, and that expression is called resultant. Given this resultant, we've already eliminate variable x and y, and end up with a single variable polynomial with respect to z, and that is pretty easy to solve. This seems quite work. It has been used in multiple different papers solving multiple different problems, and it works well in all these quite simple problems. But for general problems, it will generate quite large symbolic resultants, and it's quite hard and slow to work with. Thinking about we have a 10 by 10 problem, and it will need us to solve a 10 by 10 to compute a 10 by 10 determinant, and that's pretty time consuming. There are some advanced resultant method that can generate quite compact resultants, but one needs to pick manually and optimize it manually. One example is this BCD method that is used in this paper. Another alternative is Grobner basis. The idea of Grobner basis is we can convert a polynomial system to another one that shares the same roots, but easier to solve. For example, we have this polynomial system on the left, and the linear combination of f1, 2, and 3 can form a set in the middle, and that set contains all the polynomial systems that shares the common roots. Among all these polynomial systems, we can generate a basis on the left, on the right, sorry, called Grobner basis. It has such a nice feature that you can see the last one is a single variable polynomial that is quite easy to solve. Finding the Grobner basis is not trivial. It's time consuming and not unique. There are a bunch of algorithms that can already do that. I won't expand that much on this topic because there are a bunch of really good tutorials online. I cannot do better than them. And what I need to point out is the biggest issue of Grobner basis method is the coefficients may explode. It might generate some unstable behaviors if we use floating numbers. For example, in the code I showed here, we try to solve a looks simple polynomial system V over here. The degree is quite low, the coefficients, it's quite simple, but once we compute the Grobner basis of that, the leading term, the leading coefficients of this polynomial system is that big. You can think about if we solve Grobner basis on with floating numbers with this much of like we will lose a lot of precisions. Another issue of Grobner basis is it's pretty slow. Solving a 5 points relative problem needs 0.5 to 1 seconds, given one needs to do a lot of symbolic computations in computing the Grobner basis. So back to our chart, the general solvers, including the resultant and Grobner basis, they are not that stable. You need to manipulate your polynomials quite a lot, and it's not fast. You need to do a lot of symbolic computations, and it's quite not easy to access. The theory behind it, one needs to learn quite a lot and one needs to do quite a lot of manual optimizations on it. And it's quite easy to initialize because you don't need to know the initial solution. You don't need to worry about the initial solutions because it solves the system as it is. And it's not that scalable, as we can see in the previous example. For larger problems and for some specific problems, the coefficients may explode, and that may you may met some out of memory issue in using all these general solvers. One big leap in solving polynomial system in computer vision is the introduction of this specific solvers. The idea starts from a very simple idea that we are not solving any general polynomial. All the general solvers are designed to solve them, but in computer vision applications, we are solving actually the same form of polynomials, but has different coefficients. And then researchers started to propose an idea that one can automatically generate an efficient solver that can solve a particular problem. And this problem, the most representative one, is called elimination template. It has two steps. The offline stage, it tries to find the Grobner basis of a specific polynomial system on a finite field. It's quite easy. It's not that slow to compute, and it's quite stable because it's computing on a finite field. And after finding the Grobner basis of a simple polynomial, it remembers the recipe in eliminating variables. For example, it can remember to eliminate one variable. You need to say x times the first polynomial and then subtracts the second polynomial, so on and so forth. And then they can form an elimination template for for all the coefficients. The template is in the form of different matrices. And on the online stage, given a new problem that has the same form but different coefficients, one just need to insert the given coefficients and then solve the problem following the recipe. So it is a big leap in solving the polynomial system in computer vision. And then the offline stage is an easy to access black box. You can treat it as a black box. And the template generation is fully automatic. And the online stage is simply a Gauss-Jordan elimination and the linear system solving, which means it's really fast. And here are some quite representative problems it can solve. On the last line is the very classic 5-point relative post-estimation problem. It can solve this problem within 1 millisecond, really fast. And another problem includes 3-point relative post with homography constraint. For many problems, it can solve it within a fair amount of time. But it's not perfect. So there are problems that cannot solve by this nice technique. So we have two reasons for that. One is the offline stage still need to solve Grobner basis. It may not be achievable. You may still meet the issue that the coefficients may explode, and the template size may not be predictable, and the final template may be quite unstable sometimes. For example, for the 3-view triangulation problem, we have 3 views. On each view, we have one observed point, U1, U2, and U3. They are the projection of the same space point. And what we need to find is the point in the 3D space such that we have the point U hat 1, U hat 2, and U hat 3, they satisfy the epipolar geometry. So we can form an optimization problem that we minimize the sum from Ui to U hat I. And we have the constraint, which is the epipolar geometry, epipolar constraints. And we can convert this problem into we can solve this problem by Lagrange multiplier and convert this problem into a polynomial solving problem. But this problem, using this elimination template techniques, it will generate a template size larger than 1000 by 1000, and which is quite hard to do Gauss-Jordan elimination on this big matrix. So finally, to solve this problem on one single point with elimination template, you need around you need around half a second to solve this problem. So back to our chart. For the specific solvers, it's not that stable and accurate because still we are going to compute the Grobner basis. What Grobner basis has is still there, and it's fast since the online stage is only Gauss-Jordan elimination and linear system solving, and it's quite easy to access thanks to all the contributors. The elimination template generation now is fully automatic. And it's easy to initialize. We don't need to initialize the system. We don't need to know any close solution to the system. But it's not scalable given the previously mentioned issues. Now back to our main role is the homotopy continuation idea. The basic idea of homotopy continuation is solve the system using another problem that we know the roots. So suppose we know the solution of an quite easy to solve system g of x, and we know our target system f of x, and we can form a homotopy shown here, h of tx. We call them a straight line homotopy, and the solution of gx. Between the solution of gx and fx, there exists a continuous path between them, and we can track them. And then we can track them step by step, such that we can track from one solution in gx to one solution to fx. Then we can get all the solutions of fx. Later, Tim will give a quite general introduction to this method. So later we can see it's tracking this solution is quite simple and quite easy to implement, and we're not doing any fancy operations on the polynomials so that we can solve the problem as it is. So it's quite stable and general. And homotopy continuation method can solve all these methods with huge number of unknowns and huge number of solutions. I need to point out that this Katsura problem is a quite classic benchmarking problem in polynomial solving community. And you can look at, we have a problem with 2 million solutions, and with the very classic implementation of homotopy continuation in Bertini, we can solve that within 2 hours. And here is a comparison with homotopy continuation and the elimination template. Here are a bunch of problems with different scales, different number of unknowns, and different number of solutions. We can see elimination template did quite well on small scale problems, and the CPU implementation of homotopy continuation is way slower than elimination template. But for the larger systems, for example, 4-view triangulation and the trifocal relative pose estimation without known focal lengths, it's quite hard for elimination template to compute the Grobner basis of this system. In doing this experiment, we met out of memory issue on our computer, but with homotopy continuation method, we can solve them easily. So back to our chart. Homotopy continuation is here. It's really accurate and stable. It's not fast, and it's easy to access. Later, Tim will introduce how easy it is. And it's easy to initialize. You don't need to know the initialization value of the problem you want to solve, and it's scalable. You can apply this homotopy continuation method to a really huge problems. So in this tutorial, we are going to go towards to an ideal polynomial solver, we will focus on homotopy continuation, and we will try to solve the only drawback of homotopy continuation to introduce how to accelerate it. So I'll pass to Tim to give us a general introduction of homotopy continuation. Yes, no problem.
Yeah, is there like a presentation mode?
Yeah.
And I might click a link.
Zoom screen sharing stays on.
I think it stays on, right?
Stays on. Okay.
Stays on. I don't exactly know, but should I mirror your screen?
That would be helpful if you don't
Let
mind.
me see. Let me see how should I do it.
I'm going to show like a YouTube video for like a minute, maybe. So the link is embedded in the slides.
Okay. Hmm.
Okay, so yeah, I will try to introduce you to homotopy continuation, following up on what we've done before. Let me wait for the slide to advance. Hopefully it will. Do I click or just use the arrow keys? Oh, apparently I can go down. Maybe if I click and then hit the arrow, there we go. Ah, great. Okay, so just to sort of set the stage, I guess I'm kind of assuming some kind of background in geometric computer vision. I won't assume any background in algebraic geometry, so don't run away if yellow books are not your thing. So this talk will be broken up into two parts. So part one, before the coffee break, will be 30 minutes. I will give an overview of how homotopy continuation works from the point of view of a user and just a very basic bare bones explanation of the underlying principles. And I'll explain this in the context of some geometric vision problems that are hopefully familiar to many of you, namely perspective 3-point and 5-point essential matrix estimation, both of which featured in Ben's introductory talk. Then there will be a 1-hour coffee break. You can come ask us questions or go drink coffee. And we will resume, or I will resume from 4 to 4:30 with part 2. And I will highlight a few cool applications of homotopy continuation that have been featured at these conferences in the last couple of years. And by the way, if feel free to interrupt me at any point. I actually like this to be interactive. So if I'm talking a bunch of nonsense, just heckle me. Why should you care about homotopy continuation? Well, we heard the answer from the previous talks. There's a general need to solve polynomial systems in computer vision applications. If you're solving them in RANSAC, you need these solvers to be fast. For plenty of problems, homotopy continuation might be the only method that works. So for instance, we saw this in generalized relative pose problems from Ben's talk. I would add the following. So there are plenty of other methods where, symbolic computation methods work well. Grosvenor bases and elimination templates are great technology that you should look into. But even still, you might get some interesting information from running a homotopy continuation solver on this problem. So I'll talk about an example where that happens. Oh, by the way, I'm not a computer science person necessarily. I'm really in the math department. So why am I here? Well, I met all these wonderful people. So Ben, Hongyi, Ricardo, also Tomas Pidla, 5 years ago in Providence. And that kind of started a string of collaborations where we were applying polynomial system solving methodologies to various geometric vision problems. And I've just listed a bibliography here, which you can consult later. These slides are on the web. And so I've categorized them by subject matter with these 4 shapes. Long story short, all of them involve some sort of numerical homotopy continuation computation. And additionally, there's this notion of monodromy, which I will try to give you a rough idea of because it's an important part of many of the solvers that have been developed in the last few years. So this is where you go for more reading. So let me start with a very basic problem. So this is perspective 3-point. So we saw it in the first talk. Our notation is slightly different. So Ben's big gammas are my q's and the little gammas are p's and the rows are lambdas. But it's the same problem, right? You're trying to estimate a calibrated camera matrix in 3 depths from correspondences between known 3D and 2D points. Right, so we represent these in homogeneous coordinates. We normalize them in a clever way. And we write down our projection equations, which are polynomial in the unknown depths lambda I and the calibrated camera matrix RT. Now, with homotopy continuation, we could just solve these equations right away, or we could eliminate certain things. Why not? So the classical approach would be to just eliminate rotation and translation. This is an ancient problem, by the way. So I guess Lagrange was the first to study it in the 1700s. A little bit later than that, this guy Gruner wrote down a system of 3 equations and 3 unknowns for the unknown depths. If it looks like the law of cosines to you, that's because it's the law of cosines. So we have 3 quadratic equations in 3 unknowns, lambda 1, lambda 2, lambda 3. And there's an upper bound on the number of solutions to a system of 3 quadratics and 3 unknowns. It's 2 to the 3, which is 8. And that upper bound is tight for this example. So I'll explain how do you compute all 8 solutions to this system using homotopy continuation. This is purely for illustrative purposes. There are already great P3P solvers out there. I just wanted to make sense on a compact example that you could try at home. Okay, so what's key about these equations is they're not just depending on the unknowns, they're depending on measurements. And oh dear, my slide looks like it's kind of clipped. Is there a way to resize this? Maybe, oh. This might be okay. Yeah, well, you know, I'm okay with just doing this.
Where was it? Yeah. Wait,
Let's do it the old way.
sorry. It's because it's in the browser. You should open in the preview.
Yeah,
Just click open in preview.
I cannot find where that talk is. It should have this presenting.
Is this preview?
This is not preview.
That's the problem.
This is presenting. You should be able to.
Just scrolling is fine, just continue.
All right,
You can download.
Yeah,
I can download.
I'll just use the.
This is the browser.
Okay, cool. So equations, 3 equations, 3 unknowns, but there's something else important here. Okay, so unknowns are, I'll call them variables. There's also the measurements. So your world points, Q1, Q2, Q3, your image points, P1, P2, P3. So in the literature on homotopy continuation, these measurements are called parameters. Okay, so parameters for me does not mean something that's unknown, it means something that's given. And the main idea behind homotopy continuation is if you want to solve a system for some parameter values that you're interested, let's call them Q1 and P1. So Q is my world points, P is my image points. It helps if you already know solutions for some other values of parameters, Q naught, P naught. So how can it help? Well, let's imagine that we had something called a homotopy function. So homotopy function depends on the unknowns and a continuous parameter t. And it will have the following property. So if I evaluate my homotopy function at t equals 0, it gives me the system at the parameter values where I know the solutions. And if I evaluate the homotopy function at t equals 1, it gives me the system that I would like to solve. Well, okay, if this homotopy function is differentiable, assumption there, then we can use the implicit function theorem, at least in theory, to solve for our unknown lambdas as an implicit function of t in a neighborhood of any point where the Jacobian of the system is non-singular. That's basically the statement of the implicit function theorem. How does this actually work? Well, if my homotopy function is identically 0 for all lambda and t in some region, then its derivative with respect to t should also be identically 0 in that region, so continuous region. And I can compute the derivative of my homotopy function using the chain rule. So here's the formula. It's the derivative of h with respect to lambda times the derivative of lambda with respect to t. So this dh d lambda is a 3×3 Jacobian, okay, and d lambda dt, 3×1 vector. Okay, plus dh dt. This should be equal to 0. If you rearrange it, you can get an expression for the derivative of lambda with respect to t, and that's a differential equation. And it's a pretty simple one to solve. You just put an integration sign on the right-hand side of the equation, and that's it. So this tells you what lambda is. You integrate the inverse of the Jacobian times dh dt. Okay, the negative of that. That's pretty much it. So how do we actually integrate that? Well, there's no closed formula. You have to do numerical integration. So before I explain numerical integration, let me just state the main method that's being used all the time. So here's a parameter homotopy for a square system. That means n equations and n unknowns. And it depends on some parameters, like q and p in perspective 3-point. So there's an offline stage. This means we need to solve the system for some starting parameters. And to really make this work, the best choices is that for these starting parameters is that they have complex number entries, which are random. So in other words, you want your data to be not just generic, but also generic in the sense of complex numbers. Okay, so let's just assume somebody hands you the solutions to this random complex valued problem. So we said there are 8, right? 2 to the 3 solutions. Okay, so this gives you 8 starting problem solution pairs, right? So we have the same parameters everywhere, and then different solutions, lambda 0, 1 through lambda 0, 8. Okay, so now some genie hands you these starting problem solution pairs, and it's time to solve the real problem you're interested in, whatever came from your data. So you're given online a new set of parameter values, Q1, P1, and you are going to define the following a homotopy function, which we sort of abstractly specified in the previous slide. Here's a good choice that works pretty generally for a homotopy function. So you take your parametric polynomial system f, and you plug in for the parameters the straight line segment that connects starting and target parameters. So this has the properties that we're looking for. It interpolates between the start system that we know how to solve and the system that we want to solve. Little bit of a technicality is that it doesn't interpolate linearly between these systems because the polynomial might not be linear in the parameters. So if it is linear in the parameters, then you get a straight line homotopy. But if your original system f is not linear in the parameters, then it will not be, the homotopy function will not be linear in T. Okay. And so now we just write down the ODE we had before. We integrate it, and there are basically 8 initial value problems we need to solve, 1 for every starting solution. And then you're done. You get the 8 solutions to the problem you're looking for. Easy peasy. Okay, so how does the numerical integration work? Well, there's enough structure to this problem that we don't have to use a general ODE solver. We can actually use something that works very well for this particular kind of problem called a predictor corrector method. And it's pretty simple. So here are the 5 equations that you want to know. So here's your homotopy function, here's your ODE, here's your initial condition, all from the previous slide. And now the idea is we're going to try to estimate points along a solution curve. So here's my solution function, lambda of t. How does the solution change with respect to t? And suppose I know an exact solution at some time, ti. How would I get a solution at time ti plus delta ti, where delta ti is some step size? Well, the simplest thing you could do is use Euler's method, right? So if I want to know the value of my solution function at this next time point, ti plus delta ti, well, I just need to add on to the value of my function at ti, the step size times the derivative of my solution function, which I know an expression for. I have an analytic expression for it coming from this differential equation. So this is what's called a predictor step. And so the simplest predictor that you can use is Euler's method. In practice, there are lots of better choices you might be able to make. Fourth order Runge-Kutta method is a popular one. But just think Euler's method for now. So now what's really good about this specific ODE is that we don't just have to predict, we can also correct. So the corrector step is nothing other than Newton's method. So when I run Euler's method, I predict that the point on my solution curve is somewhere over here. Maybe it's close to the solution curve, but not as close as I want it. Well, I just do some number of iterations of Newton's method. That's exactly what this last equation is here. And that should correct you onto the solution curve within some, hopefully, small number of iterations. In fact, you usually don't want to give yourself a budget of too many iterations. So if you've ever seen these pictures of the chaos of Newton's method and fractals, you know that if you iterate for a long time, weird things could happen. So oftentimes the budget is set kind of small. Okay, most important slide of my talk. Any questions? Yeah. Yes. So how do you choose the step size? Often it's chosen adaptively. So you maintain a history of previous successes or failures. And depending on how many successes you've had, you may double the step size. Or if you fail, you may cut it in half. And there's some floor for how small the step size can get. The fixed step size is probably too slow. Or, I mean, you don't want to use a fixed step size because sometimes you might really need a small step size, but you don't want to be stuck with that. Yes,
The nature of the differential equations such that usually converges either like Euler's method or because there are some equations, other than differential equations that you will not converge with Euler's method. So does it all, is it such that the structure is such that it can always do something simple like this, or do you need like something else, maybe some implicit methods as well?
well, you certainly can use other like implicit methods, for instance, but the real problem is that whether or not the assumptions of the implicit function theorem hold or not. And so implicitly, what I'm assuming here is that the data are generic. And this actually, I'll say this on the next slide. So if you are trying to solve a system that has a singular solution, then your Jacobian is no longer invertible and no method will succeed. Yeah, question? Okay, so did that address it? Cool. Yes.
Is it axing to other solutions?
Yes. So there's a fairly nice theory that describes things that would happen if we had infinite precision to compute all of our real numbers with, but in practice, due to rounding errors, you could have two solution paths come together and things like that. Yeah.
Things you call parameters, I guess.
Yeah.
They are performing. You
Correct. Yeah, exactly. Okay, good. Yeah.
So would you always use this like 1 minus t, or is there some reason why you would want something else maybe?
Any differentiable path from start to target parameters is fair game here.
So this is like a good idea.
It could be. It really depends. I mean, we choose this because it's simple, but it's within the designer's toolkit to pick a path that interpolates between the starting and target parameters, however they like, as long as it's differentiable. Okay, one more question, then I'll finish. Yeah.
You were going to talk about the data doing this, but how important is the choice of the initial solutions that you're at the starting point? Say,
Well,
you make them random, but
yeah.
doesn't much doesn't matter.
Well, I mean, there are trade-offs that you might worry about. I mean, ideally, you would choose a starting problem that's close to your target problem. Of course, that's not going to be possible if you're going to solve something 100 times. The reason to choose things generically is because they'll have, with probability 1, okay, air quotes, the right number of solutions over the complex numbers. And the key property that you need is conservation of the number of solutions. And you want to be sure that you're taking appropriately general path in the space of all parametric systems for your particular problem from start to target. Exactly. That's right. And you can guarantee that with probability 1 with the appropriate randomization for all t from 0 to t less than to 1 minus epsilon, let's say. Because if you're solving a singular system, then there's no hope. Okay, so this is predictor corrector. Okay, I didn't address how you solve the starting problem, right? So how do we get our starting solutions in the first place? So I'll try to explain this idea of monodromy. Here's the process. You will, to find the starting solutions, you will fabricate or synthesize what I call a random problem solution pair. So in other words, pick a random scene, pick a random camera, compute your depths, compute your projections. And now you have one problem and one solution. You need to get the other 7 solutions for that problem. And the solution, the way you get those other 7 solutions is kind of silly, to be honest. We already explained how this parameter homotopy works. So you can track from this problem solution pair to some other problem, and then go to some other problem. and then go to some other problem and then come back. The problem you started with. And believe it or not, you will often get new solutions by doing this. So this is the idea of monodromy. So in fact, at least for this specific example, you can find all solutions this way. There's a technical reason why this works. The parameter space for your problem is connected. That turns out to be the case actually for a lot of vision problems. Let me show you a video of monodromy. So let's go even more basic than P3P. Suppose we just want to compute the square roots of a complex number P. So I have one parameter, P, and one unknown, X, and I want to compute the square roots. Oh dear, it seems like my the link is no longer embedded in the slide. Maybe I'll show it during the break. How about that? Okay, so maybe when we resume, I can show you how this permutation works. But the important thing about monodromy is that this is an offline method. It gives you the starting solutions for a random problem, and you only have to run it once. And there are some other nice things, which is that it can be useful for exploiting symmetry. The nice thing about P3P, which came up in Ben's talk, is that there's a symmetry to the problem. We know that if we have one set of depths that satisfies these algebraic equations, then negating those depths also satisfies those equations. That's something you can exploit when using a homotopy continuation solver. And actually, this monodromy method will give you some clues about whether or not you have that symmetry or not. So that's kind of a powerful thing to know. Okay, some remarks and caveats. So there are a lot of numerical subroutines that can be tweaked in homotopy continuation. So the step size control, predictor method, pretty much everything still works for systems of rational functions. So, rational functions are like polynomials once you clear denominators. As long as your denominators aren't exploding, you should be able to solve those as well. Okay, but coming back to some of the questions we had earlier, we are assuming that the input data are sufficiently generic so that our Jacobians are never singular. And if you have a special case, like 3 coplanar points in P3P, then this assumption might not be satisfied. You might need to construct a different solver for that special case. Okay, and there are other issues due to numerical, due to the nature of inexact numerical computation, where the theory doesn't always explain what might be happening with your homotopy continuation solver. But nevertheless, there are a lot of software implementations and general purpose software packages, which can solve systems quite reliably with, let's say, less than 100 variables and thousands or even millions of solutions. So there is a demo, which I'm hoping to show. If you go to the website for our tutorial, there's a demo you can run using the computer algebra system Macaulay 2 for how to solve the 5-point relative pose problem. And you don't need to install anything, it'll just run straight in your browser. So hopefully I could show that after the coffee break. But none of these are really suitable for Ransack. So if you need something that's like really fast, then you have to talk to Hung Yi, you have to talk to Ricardo, and get some of these libraries that do a lot of really clever things to make tracking faster. Okay, so I'll conclude with 5-point problem. This is, again, just an illustrative problem. We don't need homotopy continuation to solve this. Nister's algorithm, Nister's Stuvenius method, works just fine. But I just want to illustrate concepts. So hopefully we're somewhat familiar with essential matrix. It has 9, it must satisfy these 9 cubic equations we saw earlier, the de Mazur constraints. And additionally, there are 5 constraints which depend on the data, or parameters, as we say. And okay, there may be one more equation you need to fix the scale of the essential matrix. And how you do that is not so important as long as the data are generic. So you could set the first entry to be 1. Okay, if we count the equations and unknowns like we were doing at the beginning of this tutorial, then we see we've got 9 plus 5 plus 1. So that's 15 equations, but only 9 unknowns. Okay, that's no problem for Grubner bases. The Grubner bases are equation-hungry methods. More equations are maybe even better. Is this a problem for us, though, that we have 15 equations and 9 unknowns? If we want to use a homotopy continuation solver, the answer is no. So the trick is, if we have a random problem solution pair, the parameter homotopy method is going to work, generally speaking, if these two rank conditions are satisfied. So the first rank condition is that the Jacobian of our system with respect to the variables has rank 9 at the problem solution pair. The second condition is that the following augmented Jacobian, where you have the derivatives with respect to parameters and unknowns, also has rank 9. What this first condition means is that there's the solution is isolated. So E star is an isolated solution for your system specialized at P star. And this rank condition means that a generic problem solution pair is in fact solvable. So that's an important property to have, because even if you know that your starting problem and your target problem are both solvable, you don't necessarily know that the intermediate problems are solvable, have an exact solution. And so when you check that this augmented Jacobian has rank 9, that's essentially what you're doing. It's the I mean, this is just an automatic way of counting parameters and checking your problem is minimal. But you don't even have to know about all that stuff. You just compute the rank of this Jacobian, and it'll tell you. Okay, so rank equations can be used to check that a problem is well posed. And so we can then use parameter homotopy using just a full rank subsystem of F. So in other words, I have this 15 by 9 Jacobian matrix. I pick any 9 equations which give me a full rank submatrix. Those can be used in a parameter homotopy. And that subsystem may have other solutions, but it turns out that they don't appear when you use this method. So more formally, the excess solutions to the square subsystem are not connected under monodromy permutations to any of the 10 solutions which satisfy all 15 equations. So that's the one kind of nice thing about homotopy continuations, that you don't have to use all the equations necessarily. If you have these rank conditions holding, then you can just fabricate an initial problem solution pair, check that these rank conditions hold, choose a square subsystem of full rank, run your parameter homotopy. All the other constraints you ignored will be satisfied with probability 1. It's a little bit counterintuitive, but you can check that it works, and we will check that it works on this demo. Okay, so it's break time. Go get your coffee in the other building. Come ask us questions. We'll resume. Okay, so I think we'll resume with part 2 of the tutorial. Thanks all for coming back. So like I said, I'll talk for another 30 minutes about the basics of homotopy continuation, as well as talking a little bit about some research papers that use these techniques. And then Ricardo and Hongyi will get into some of the details of how you build extremely efficient versions of these solvers. So for now, we're just doing basics. Now, I got a good question during the break, which is about this monodromy thing. So finding new solutions starting from 1. How does that actually work? And so we have an animation that shows this to you in a very special case where our problem is a complex number P, and our solutions are the square roots of P. So if P is equal to 1, then X must be equal to 1 or minus 1. So in the upper panel, sorry, let me say the lower panel represents the space of problems. And so the X and Y axis are the real and imaginary parts of P. And if our if our problem travels around in a triangle in this parameter space, then this loop in the space of problems induces a path in the space of problem solution pairs, which you can see in the upper right panel, or sorry, in the upper panel. I'm just showing the path of the solution. So starting, oops. So starting from an initial problem solution pair, which would be like P and X are both equal to 1, that would be here. As we move around our problem in this triangle, we find solutions to new problems. And then eventually, we come back to the problem we started at. But we trace out this arc that looks like this in the space of solutions. And that takes us from the first square root, x equals 1, to the second square root, x equals -1. So all of this is to say that traveling around in random directions and coming back to where you started in the parameter space has the potential to find new solutions. So it's true that if you were to go this way and then come back, you would just get the solution you started with. But the point is that you want your loops to have a reasonable chance of encircling some problem singularity. The singularity, in fact, is just where P equals 0, and there's only one square root of 0. So this picture is monodromy in a nutshell. Starting from one problem solution pair, you can find other solutions for that same problem. Okay, everything we do is, kind of like this. Okay, and now I'll show you a quick demo of solving the 5-point problem, which we concluded our talk with. So this is using Macaulay 2. It's a software package that does Grubner bases, but also homotopy continuation. And you'll see that the workflow is not too involved. So we load our package, we set up our equations, we have these Demazir trace constraints, as well as our epipolar constraints. This should be equal to 0. And then we have some normalization for the essential matrix. So we'll actually just introduce a new parameter, S, to represent the sum of the essential matrix entries. And so all these lines of code just write down these equations in a format that's, in data types that will be used in homotopy continuation subroutines. By the way, if you want to run this tutorial yourself, you go to our tutorial website and you find my slides and you scroll to the break part of the slides and click the embedded hyperlink. And you can upload, there's a markdown file, you upload it to this website and you run it yourself. No installation required. So you set up the equations. And now you write a function that synthesizes a problem solution pair. So here's a function called synthesize. The syntax is not that important. All it's doing is generating random points in random camera and computing the associated problem solution pair. And it takes an argument ff. So ff could be the real numbers or the complex numbers. And when we do this monodromy, it's best to synthesize a problem solution pair over the complex numbers.
Why?
Why? Well, because you want your problem to be in general position with respect to the one you already know how to solve. And so if you have two real problem instances, let's say you want to track a straight line from one to the other, there's a good chance that you're going to hit a singularity in the middle of that path. However, if you have a path in the complex parameter space, then the chance, if you have a random complex starting point, the chances of hitting a singularity in the middle are practically 0. That's the reason. Good question. So we fabricate an initial problem solution pair over the complex numbers. And then we do some sanity checking, check that the ranks of our Jacobians are what they should be. And like I said, this is a minimal problem. So all that we have to do once we know that these rank conditions are satisfied is extract the square subsystem, and we can use that inside of our parameter homotopy. Okay, so now it appears, so this line I just ran here actually does the monodromy computation for you. And if you wanted to see what all of these solutions look like, oh, I'm not even going to try to type. There's a list of 10 solutions, which you can see if you scroll all the way to the right. So 10 complex essential matrices associated to your initial problem. And so now what we'll do is solve a new problem. So let's randomly generate some data over the real numbers. And we'll also generate a solution, which will be the ground truth that we're trying to recover. So that's Sol 1. And all we have to do is specialize our parametric segment homotopy to the starting and target parameters and track. So this function track homotopy just numerically integrates the ODEs that we saw before, and it gives us a list of target solutions, which I called Sol 1s. And so now we'll just check in this list if any of them are close to the ground truth within 10 to the -6 Euclidean distance. There's one. So we got the ground truth. Okay, this is sort of minimal workflow that you might want to do if you're using a homotopy continuation solver. So again, this is on our tutorial website. You can run it in the browser. Contact us if you get stuck. Okay, now I'll switch to my slides. I shouldn't have clicked. Oh, thanks. Great. Okay, so in the remainder of the talk, I'm just going to give some research highlights where homotopy continuation was useful in some papers that I've written in the last year. So I'll talk a little bit about 2 papers that are at CVPR this year. The first one is on auto-calibration. So if you're interested to learn more, come to our paper, to our poster on Wednesday afternoon. So the setup is as follows. We're given 5-point triplets in 3 views. So it's a trifocal problem. And what's unknown are the depths and the rotation and the translation. Also, the world points are unknown, and there's a calibration matrix, which is unknown. And there's some things we know about this calibration matrix. Namely, it has 0 skew and the square pixels. So the focal lengths in the X and Y directions are the same. And what we're really interested in this problem is to recover the calibration matrix. But our approach is a little bit funny in the sense that we'll actually recover some things involving depths as well. So here's the constraint we use in our paper. So Andrea Porfiri Sin is the first author, and he'll tell you more about it tomorrow. So these are depth constraints. They just tell you that the distance between any 2 3D points is the same whether you compute it in camera frame 1, camera frame 2, or camera frame 3. So these distance constraints are not quite polynomial, right? So they involve the inverse of the calibration matrix. But I told you earlier that rational functions are usually okay. And yes, we can indeed solve these equations with homotopy continuation. If we count the equations, how many do we get? Well, there are 5 choose 2 choices for 2 different points. So that's 10. And then there are, if we're comparing view 1 to view 2 or 3, that's also a choice. So there are 20 equations plus 1 to kill the scale ambiguity. And there are only 18 unknowns. There are 15 unknown depths and 3 unknown entries of the calibration matrix. So this might look similar to the case of the essential matrix, where we had more equations than unknowns, but I just showed you we could solve that just fine. So is it the same? Can we do the same thing here? No, there's an issue, which is that the rank of our augmented Jacobian is bigger than the number of variables. That means the problem's over-constrained. So in other words, even if I have a starting problem and a target problem that have an exact solution, the intermediate problems that I solve with this homotopy are not solvable. So there's no continuity of the existence of solutions. So we seem to be stuck because this is an overconstrained problem. Now, it turns out not all is lost here. What you can do is you can drop equations like before, but now you have no hope of enforcing these for the intermediate systems. So we introduce a technique that we sort of are calling minimal relaxations, but I mean, this is sort of how all minimal problems work. At the end of the day, you drop some constraints and you give up on enforcing them, and you just deal with whatever constraints you have left. There are many different types of minimal relaxations for this problem. So basically, you can organize the different ways of dropping depth equations with these tricolored graphs. So we enforce, a black edge means we enforce distance constraints for views 1, 2, and views 1, 3. A red edge means only for cameras 1 and 2, but not 1 and 3, and so on and so forth. And so each of these different subsystems will give us different numbers of solutions. So that's a feature of over-constrained problems, is if you start relaxing them, there are different numbers of solutions that you'll get, unlike the case of a minimal problem. So in this particular case, the minimum number of solutions is 16,000, which seems like a lot, but the maximum is like 100,000. So it could be quite a lot of variance in between. It seems like a lot of solutions, but nevertheless, Andrea was able to apply this in some novel auto-calibration scenarios and get pretty nice experimental results. So come learn more about it on Wednesday. Okay, the second application I'll tell you about is absolute pose. So this is like P3P, but there are points and lines now. So you might have 3D, 2D correspondences between lines as well. And maybe mixtures of points and lines. So this absolute pose problem will be minimal if the number of points and lines is 3. So the total number of correspondences is 3. So P3P is when you have 3 points and 0 lines. And then there are these other cases like 2 points and 1 line and 1 point and 2 line and 3 lines. And it turns out that this monodromy thing I showed you an illustration of can also give you some clues about symmetries of your problems. And I won't explain exactly why that works, but you can read this paper that we had published in the SciAm Journal of Applied Algebraic Geometry. If you really want to know. The punchline is that as a byproduct of this monodromy computation, you'll get information about the symmetries inside of the system. And what we were able to discover is, okay, it's well known that P3P has the symmetry where lambdas go to negative lambdas, but actually the cases with mixed point and line features have a symmetry as well. As for the case of 3 lines, there's actually no symmetry. So this was a useful observation. So in another paper, which you can learn more about on Friday morning, Petr Hruby is the first author. We applied this insight to design symbolic solvers that were better than the state of the art. So the previous solvers, actually, there's this funny quote in one of these previous papers where they say, although we do not theoretically prove that our solutions are the lowest possible degrees, we believe that they are, and they give some justification for why that's true. They think that's true. Well, it wasn't true, actually. So in the case of 2 points in 1 line, instead of solving a quartic, we can solve a quadratic equation. And as you might expect, that's faster. Similarly, for 1 point and 2 line, degree 8 goes down to degree 4. Again, faster. Degree 4, you can solve in closed form. Degree 8, generally, you cannot solve in closed form, but for this special case, there's a symmetry, and you can. So go talk to Petr on Friday morning to learn more about that. these are kind of cute examples, right? Like we're reducing degree 8 to degree 4 and degree 4 to degree 2. What's is it really that significant though? Well, last year at CVPR, we had another example of this type, general flavor, where we were interested in a relative pose problem that when we wrote down the polynomial system of equations, we saw it had 3,584 solutions. That seems like kind of a lot. But we could reduce it to solving a sequence of subproblems where each subproblem had a much smaller number of solutions. And in fact, everything had 2 or 4 solutions except for one problem has 28 solutions. And I'll try to give you an idea of what sort of analysis goes into discovering this. But the bottom line is that you reduce the complexity of homotopy continuation from tracking 3,584 paths to tracking just 28. So that's a pretty big saving. So the idea behind this problem is instead of a 3x4 camera matrix, you have a 2x4 camera matrix. And the reason why this is interesting to people is because they want to model radial distortion. Or rather, they would like to estimate cameras that have radial distortion, but not actually model the radial distortion. So basically, the idea is if your image distortion is radially symmetric around the center of the camera, or sorry, around the center of the image, then the point that you measure is going to lie along a line that connects the image center to the idealized perspective projection. So in other words, this A times Q is my idealized perspective projection, and the 0, 0, 1 is my known image center. Well, another way to parameterize the line spanned by these 2 points in the plane is to just take the first 2 rows of your camera matrix and zero out the third one. So the line spanned by this point and this point is the same as the line spanned by this point and this point. So in other words, if you only care about the radial line that connects your image center to the perspective projection, you can parameterize that with the first 2 rows of the camera matrix, assuming your image center is the origin. So that's the idea behind using this 2x4 camera matrix, which is called a radial camera. And it can be seen as a relaxation of the pinhole camera model. Okay, so classical epipolar geometry, we know we need 2 eyes to see depth. For radial cameras, you need 4 eyes. And this was my best attempt at producing an image of a creature with 4 eyes. It's from some medieval book of alchemy, if you are curious about where it came from. But you need 4 radial cameras in order to recover a world point, basically because the back projection of basically because you're intersecting planes in space, and 3 planes are always going to intersect, so you'll need a 4th one to recover the point uniquely, right? So the back projection of a point under the radial camera is not a line like it is for the pinhole camera, it's a plane. So you back project with the first camera, you get a plane. You cut it with another plane, you get a line. Cut it with the 3rd one, you get a point. You only get a constraint with the 4th plane. Okay, so there is something kind of like epipolar geometry for this radial camera. It's what's called the radial quadrifocal tensor. So it's quite similar to the quadrifocal sensor from Harley and Zisserman, if you're familiar with that. But what's important is that although there are 3,584 solutions in the different camera matrices for this radial camera problem, they map onto just 28 solutions in the quadrifocal tensors. it's kind of like the situation with essential matrices where you may have 40 solutions and rotations and translations that map onto 10 solutions and essential matrices. It's just happening on a bigger scale. And so what's nice about parameter homotopies for solving this problem is you don't have to explicitly write down the constraints on these quadrifocal tensors. You're able to just solve it using the formulation in terms of camera matrices. You only have the key thing that homotopy continuation buys you is that you can track one path per quadrifocal tensor and recover all of the different cameras that map to the same quadrifocal tensor later. And that's why you get to track 28 paths instead of 3,584. So it's a big savings. I mean, it makes the difference between being able to solve this problem in a reasonable time and not being able to do that. That I think is where I'll end. So there are reasons to be optimistic about homotopy continuation. Symbolic methods are good for a lot of problems, but homotopy continuation scales to problems with more solutions. Not all applications require ransack runtimes. Even if you're not using a homotopy continuation solver at the end of the day, you could still want to use it for other reasons, designing other solvers, finding symmetries, as fallback methods when standard methods fail, and measuring algebraic hardness of problems. So the exciting future work, well, there are lots of things. So ways to improve efficiency, something I didn't talk about was learning starting problem solution pairs. So this was another joint work with Peter Ruby 2 years ago. And parallelization in GPU, which we'll hear more about in the next talks. So thanks very much.
Which happens to be discovered by hand. Sure. If they did like work which is more detailed around find like groups of paths, it could enable you to automatically find subsets.
So it's partially automatic. The monitoring computation will tell you which solutions belong to the same groups.
Yeah, so I'm Ricardo. So all of this, so this research and writing fast solvers came about when I wanted at one point work with Thomas, and Thomas was actually said, "Oh, I'm going to Brown," and I went to Brown, and everything started, and we met and we started this. So so the idea is we are going to talk about design principles in general. So what can we say in 20 minutes that's going to be useful and give you a comprehensive overview of the intuition behind all the different issues that can affect the speed of the algorithm. So I'm going to basically give a recap of what Tim already talked about, but in a more intuitive way. And at the same time, we're going to see how the ODE solving along level sets works, which is the differential equation that he talked about. And we're going to talk about predictors and correctors, and what are the intuition behind the different choices that you could make, and why did we make the choice that we have right now. So then we're going to talk about code level optimizations. So Minus is a C++ framework that I wrote that you can use to in C++ to have templates to help you code fast solvers in a way that's correct and in a way that's allows you to try different options. And it's very highly optimized. So, and then we're going to have a closer look at key techniques. Yeah, so this image I just typed in DALL-E, show me homotopy paths in a square. That's what it came. All right, so yeah, so talking about numerical algorithms in general, I mean, this is interesting because we are bringing more of a numerical type of algorithm to solve these types of problems. And so what are some design principles that we can have for numerical algorithms? Numerical algorithms are not easy to implement, but they are generic. So that's the interesting thing. But at the same time, being generic, it makes it hard to optimize. You have to really know what a lot of details to make it optimal. So the design principles are speeds of the essence. So we are trying to optimize here for speed. So you can, when you going to read about homotopy continuation, a lot of the papers are going to give you thousands of methods, but they have different goals. So you have to keep that in mind. Our design goal is speed. We want it to be used in real-time AR and autonomous cars. So the second design principle I would say is that floating point is powerful. So if I wouldn't call it design principle, but it's more of a design choice why we choose this. So continuous modeling to design algorithms is very powerful, right? Because you bring to the game of camera estimation and autonomous car driving and everything. The self-localization, you bring to the game all these powerful tools of dynamical systems, ODEs and PDEs. All of these have to do with homotopy continuation. So, and floating point is on the rise with GPUs, right? Everybody's now having thousands of GPUs, and floating point modeling is of interest not only for homotopy continuation. So that's very important that we get into these numerical methods. So main point of a design principle, at least for my C++ package, is that the idea is that to have a really fine and good numerical algorithm, you have to be able to get inside the black box. It's not just running eigen or some fast library or LAPACK and expecting that it's going to be fast. You have to, at some point, it's going to be slow because you want it to run like a video game. You want it to run 60 frames per second, and at some point you're going to want to get inside the black box. And how to do that is the goal. So this package allows you to progressively specialize homotopy continuation to optimized versions of it in multiple layers, multiple steps, And then at each step, you add something that makes it faster or a little bit more complicated. The problem with numerical algorithms is that they become too generic, right? Like I said. And sometimes you just pick the simplest possible algorithm, let's say partial pivoting or LU decomposition with partial pivoting. That's used in all of the structure for motion packages that we have, and it's used from Eigen. Even that is very simple, but it's still too generic, right? Because what's the pivoting structure of your matrix? What's the orders of magnitudes that you can have in each of the different rows of the matrix? So that kind of stuff is very important to make it run in real time. So the problem with the smart algorithms, on the other hand, is they are highly constrained by high-speed requirements. So you can make a smarter algorithm, but then if it uses too many evaluations or some other, if you don't do it really well, it's just not going to help. So the idea is how can we try to do the third bullet and get it working correctly and make it fast. So I'm going to give you the intuition behind what we were talking. Hello? Hello? Hi?
There you go.
Okay, thanks. Okay, sorry about that. So yeah, so let's have an intuition about what's going on. So let's see. So what's happening? So let's think about nonlinear equations, not polynomials for now. Nonlinear equations is useful for everything, right? So what we want? We wish to design a fast solver for a system of nonlinear equations. So this f of gamma, f of lambda is the same notation that Tim was using. So you can have any number of equations. This is vectorial, and any number of unknowns, right? So you want to find the vector lambda that zeros this function, right? But now, not just you want to find that, but you want to do that for f in a family. For example, for any f in a family, you want it to be fast. So every function, every f for the 5-point algorithm, or every f for the same problem, that you can call it a family, right? So this is the simplest way I think of thinking about it, instead of thinking about the coefficient of polynomials. You just think of the family. So you want to be able to solve efficiently for f in a family. So if this is a minimal problem, then this is going to be a square system, right? So let's try to analyze what happens with this homotopy business if it's 1 by 1, right? In 1 by 1, and in reals, let's just not go too complex right now. What happened? You just have this graph, blue graph, and you want to know how many times it intersects the x-axis. So for any f in the family, whatever family it is that we have, of the same that solves the same type of problem for different parameters, we will have isolated solutions in general because it's a square system, right? So what happens here is that when we do what we were calling the predictor corrector design, what does predictor corrector does? So it's just traces level sets with ODE integrations. So it's important to keep that in mind. It's tracing level sets. So here you have we may locally trace a curve in a family of systems by introducing an extra variable t, right? So you have the original family of system that solves this class of problems that you're interested in, and then you just use an extra variable to locally generate trace a curve in that family, and the value of f will not depend on t. Okay, so you have a family f. And now locally you can call that, instead of using the same symbol, you can call it h, right? So now if you parameterize that family of polynomials or family of functions by t, now you can write it, instead of being this system here, f of lambda equal to 0, it's h of lambda of t and t. And this only works locally. So what happens is that this h, right, is like the f, but with the t in it. It's going to be a function. It's going to be a function. So here, the function is like a real function, like f of xy. When you have f of xy, you think of a surface on top of xy, right? So our x and y here is t and lambda. Right? So now, what we have with h, since it's 1 by 1, h is going to be a real number. So what we have is like an image. The image plane is t lambda, and the value of lambda is going to be a surface coming out of here. And that surface, you want this, you're going to want that to be 0. So you want to find where all these families parameterized by t intersect the lambda t plane. So why is that important? So let's take a look at this little part. So what happens is that you can pick if you pick any 2 points in t. So here it's like t0 and t1 from the homotopy, or 0 and 1 that we were using. So if I have, I don't know what is the level set. There's a function here that intersects this plane. I don't know where the level set is because I only have the equations. But if I happen to know one of these points, I can find any other point by continuing along this arc. So what happens? So locally we have on the right side that we can build locally a function, literally lambda, which is the solutions are a function of t. But globally, it's much more complicated, right? So this gives us an idea of what are the paths that we're going to try to track. So before we had all these homotopy paths that we were drawing, but now we're just picking one of the paths. And so so given that I know one of these points, how can I get to this other point as fast as possible? How can I do that as fast as possible? Well, if I had some kind of equation for this blue curve, I could have just gone directly to the other one, but I don't. I only have I have a global equation, which is h of lambda t equal to 0, which gives me the function, the surface that intersects this plane. And that's all I have. So, and that doesn't tell me how to walk around that. It just tells me a global description of this level set. So one idea then is to, if we start at one of these points, why don't we just write a sort of, if I know where the other point, I want to go to that other point, I can try to write a differential equation that will describe this arc in the bottom we'll describe that arc in the bottom as with a differential equation. So we can track that equation. So the difference between the regular ODE is that we have that equation of that arc, a differential equation for that arc, and we also have that arc is equal to 0 globally, like, right? So from those 2 points, how can we start doing a fast algorithm? So we could start from that point, the first point. We could go along the tangent direction, and we usually draw that tangent as a straight line, and that tangent I'm just describing as a differential notation. It's not the lambda over dt. It's just differential lambda, differential t, represented that as a vector centered at the point that we are analyzing. Right. So then, given that vector, I can go a little bit in that direction, which is one way of doing a predictor, and then I can correct it, right? So geometrically, when I correct, if I go a little bit in the tangent direction, it's just an approximation. Then when I come back, ideally I would geometrically you want to go to the closest point on the curve, not on any other point. So what happens is that usually we go back to this line over here, right? So this is the fastest and most robust is simple RK4, Range-Kutta 4 standard and Newton's method for that. But we can, a lot of other things can happen. We can also use higher order predictors. But what's the problem with that? So that's here, this line is just the derivative of the age function of our equations in terms of t. That it's just one of the tangent directions there. So if we in the polynomial case, it's nice because we have with these evaluators, they're symbolic. So we compute those symbolically, right? And then we come back to that variety. So what happens is with this part here, Newton's method, it's that Newton's method is gonna try to, when you're out here, there's a function here, a value that's not zero. So it's zero only here and it's not zero here. Now you want to zero it down, right? And we already saw how it goes. It just goes along tangent directions. So right here, there's going to be a function. It's going to go along there. But there's also other ways. So there's a problem there. That's if Newton's method, if that tangent is too far from the curve is curving too much, then you're going to be not close enough. So we have to be close enough to the curve after the arrow for Newton methods to converge fast, right? It converges very fast, but you have to be very close to the curve, right? So I just want to, so what are the things that can happen? So if this has a high curvature, right? Another problem that can happen, it can have numerical noise. And that's a big problem. I think that must be understood. This function looks all, oh, it's polynomial and it's all continuous, but it can have, but it could be algebraic like that, and then the Newton's method might just diverge. So that's an important thing to keep that in mind. So also, what other things that can happen? These curves, they may intersect or have a near intersection. So this near intersections actually happens. You can have like that, right? So it would be one point here like this that is not a function like that. So it does not have a nice tangent direction. Right? So you can have that. So these are cases where the algorithm starts getting slow. So we have to be fast in these cases. We have to kind of be fast in these cases. So that's how can we relate that to Jacobians, for example? But before I go there, what else could you do in terms of RK4? So what we call this predictor, we just draw a straight line. What are the things we could do to predict? You could also use a higher order approximation here. But what difference would that higher order make? It probably might bring Newton's method closer to the fast conversion, to the quadratic conversion, or it might bring it closer to the faster conversion part. Or also, if the curve has numerical noise, so if this curve is actually not differentiable numerically inside the computer, we might want to average different directions in the computer and average tangent direction, for example, right? So in that case, that's why we call these Range-Kutta and these predictors, they're called smoothers, right? So people that are hardcore numerical analysts, they call this a smoother. So we have a problem, we have this thing full of noise, Newton's method is gonna just diverge or converge very slow. then you want to kind of smooth it, right? So that's the idea. And I think this is useful for many other visual problems as well. So let me just finish with this this part of to tell you what's the problem with the speed is this exactly what we're talking about. So we built this linear approximation. So we have this h, which is our equations. We want it to be 0. So this h is just a surface that's coming out of the plane that intersects at that curve equal to 0. So then you take the linear approximation, which is the differential. Then it's going to be the Jacobian. So this partial derivatives there, you can take of them in higher dimensions as well. Everybody's used to that. It's going to be just Jacobian in lambda and the gradient in h, or right? This could be complicated if it's complex, because inside minus, it's actually, the matrix is complex. So the Jacobian is complex to avoid the singularities in the, hello? Yeah, so why is it all complex? Because we want to avoid all these singularities, like this one as well, in a sort of a random way. So here, when we are in the plane, right, we are restricted to some curve, and what we can do to get to this point, we might want to go here. What can we do? Or we could go around here. And maybe if I go around here, oh, I hit the singularity, it's going to be slow. But if I go directly, it's going to be smooth, fast, right? So that kind of stuff, like if that's when we use complex numbers, sort of like to make this have more degrees of freedom so that we can make these guys be very sparse, so that almost all directions that you go, you're not going to hit them. But the thing is, what happens if you hit them close enough? So that makes the algorithm be fast or slow if you can predict the kind of thing. So then, this is the complete Jacobian, which is the notation for it. What happens is that I give you a vector, which is this, and then the approximation for the surface that we have, the level set, is going to be just a matrix times this vector, right? Now, you just set this to 0. That's your ODE. That's the ODE that Tim showed. So we have, but this is like a homogeneous way of saying it. Matrix of partial derivatives times vector equal to 0. So you want the vector is that 0. That 0 is this Jacobian, right? So why? Because here you know that there is one direction where this, if this is a line and approximates this function, you can say that this line, that the function h that's here, it's 0 on the line, right? So there you want is, if it's the curve is like this, you're gonna have one guy that zeros this multiplication. So you're gonna have, but if you have multiple, there are gonna be many vectors that you give that's gonna, when you multiply by the full Jacobian, it's gonna be 0. And they're linearly independent. So that's one way of doing the analysis, usually stability theory or bifurcation theory. So that's what happens. So the linear approximation to the h, so linear approximation, so when you have that, those branches, the linear approximation that we have gets singular. We can also think that the curvature of the embedding function of that surface, that the embedding surface, that this is a level set, you can think of that near here, it's going to have high curvature outside of C, right? So that gets complicated. The rank condition number, you can use a rank or condition number or determinantal conditions to actually try to spot where these problematic functions points are. There are some methods that for polynomials are using Padé approximates to try to figure out, or at least control the step size that you go based on how close the singularity is to you. The simple numerical methods that we are using at the moment, they're fast, but they slow down near these singularities. And it actually happens more often than one would think, even with really high dimensional complex, multivariate complex space. So the problem really is when the rank drops. Like everybody thinks of the rank dropping, but this is a way of thinking about the curvature of the space of system and what people, and also the condition number is just a way of expressing this curvature and that has to do with relative numerical errors. It's just a ratio of the singular values instead of you see the rank is drops means determinant equal to 0. Determinant equal to 0 never works in numerical analysis or numerical, especially since we're solving linear systems a lot. So we use condition number to monitor the determinant and not the determinant itself. So that's because of the way the numerics works inside the computer. So adaptive step size also, we're using a simple one, which is fast, but is also too simple. And it clearly has problems because we're doing 4 Newton iterators at most, Newton iterator iterations, and we're using just simple step size control. So if we basically the step size, a simple way of thinking about it, like this talk is about, is that if you, what happens is that this guy might have some numerical noise or high curvatures there, right? So when you take a step size here, right? If you take a step size here, and the Newton's method just diverges or goes crazy, then it's going to go here. Let's say, right? So it goes here, then instead of the Newton's method coming here, it's going to go here. If it goes here, the function is high. This function is 0 here. The closer I get to it, it gets 0, right? So then it's going to go far. So you monitor, you say, I take a step, and then I see if my function, after I applied my 4 Newton iterations or 3 or whatever, did the value actually decrease? Did it go to 0? Did it not go to 0? Because there's some numerical, the Newton's method didn't actually work as you think it would, right? So these are actually the cases that happen. So you always think about, oh, it's not just dropping in rank, but when the rank is close to dropping, right? So so like this near intersection. And another problem you can also see here, because usually this near intersection is depicted as something intersecting here close by because you're doing an arc like that or an arc like that. But if you're doing an arc like this, what happens? When you do an arc like this, it's not a function of t anymore. As it's not a function of t anymore, as you go here, it's going to be, the tangent's going to be going to infinity. So that's also is actually a problem. So and it's all approximate. So how can we? It's a big question. There's people that believes in these types of methods, of numerical methods. There's people that do not believe in them. They think it's not. But I think if you actually make it work well, and you have, I don't know, I think like spacecrafts use that kind of stuff, right? So I think it could work. I think I'm taking too much of your time, but I'll talk about the package in the next talk, okay? And this is the takeaway message is that there is a lot of room to improve homotopy continuation methods. There's a lot of room. I think what we're using currently is it's fast, but it's not the best way to do it. So the randomization is not the best. Using uniform distribution for for randomizing your algorithms is clearly not optimal. And also, if this is complicated in one by one, imagine in complexes. So interpreting this in the complexes is also a problem. All right, thank you. Okay.
In other solutions like in cross-space methods, optimizations with political behavior functions, avoiding this like. And it's about also the fact that you're working with phenomenology, and how much of that being explored in I'm not really sure why. Yeah, it does seem like this is actually bipolarity. Yeah, it seems very loss of a function just because of bias when you it seems very that should help to know what you're going to do seasonality. I don't know.
It's my problem with Charles Ranford developed one of the books about homotopy. He said the first thing that you work on this problem, the first thing to try is the predictor that with a physics fly.
Yeah.
Yeah. I was thinking, going back to the report, when you have detected singular, you could probably locally desingularize using a burger to try to decide. I mean, it would have almost deciding of which. But I don't know whether it would be practical to implement.
There is something kind of like that called the thin game that people use to estimate solutions. Just to try to-
It's very well, it's classical tool that you like geometry and the blowing up
Yeah,
to separate the branches.
yeah, exactly. So they do some kind of low to low up.
Yeah.
And then make the solution.
But I think you trust the I think it will work. Because the user this to me, I mean, it allows your this to make the size of all the steps.
Yeah,
Because what you do is very primitive. I mean,
Right.
It's good at the original like a little bar four method. I mean, it's designed for a reason.
Right.
It's to solve this non-linear problem.
I guess one possibility is that maybe the steps that's messed up. I can't say that for sure.
I mean, it works quite well.
Sure, yeah, but I mean, since you're tracking so many paths, you really want each step to be as big as possible. And,
One thing that limits a lot is because you don't want to evaluate more, no? The more you evaluate this, evaluation doesn't have to touch. It totally depends on the gradient. I mean, if the gradient is very shallow, I mean, you might even do big steps in the wrong directions, and it will just, it will throw you out. That's it. So you need to be able to do some kind of clever optimization to do the dimensionality reduction of your Jacobian, and then also to find the most kind of steep gradients and go there. Yeah.
Guys, I think. Enough talk? Yeah, sure. Yeah, sorry. So, me again, and my talk is related to, thanks Rick, to introduce all these kind of things in optimized homotopy continuation. This is another perspective. It's homotopy continuation meets GPU. So, we all know homotopy continuation. We learned from Tim's talk. It's quite simple and quite straightforward. There are a bunch of existing implementations out there. For example, PHC Puck and Rick's minus, and in Julia we have a homotopy continuation.jl and a lot of the others. It's simple and able to solve nearly all sides of the problems, but it's not efficient. And from that chart I've shown before, it's homotopy continuation compared with a elimination template on small problems. It's hundreds of times slower. Okay. And how are we going to accelerate by quite straightforward parallelization idea? There are a bunch of implementations out there. Implemented this multi-threading path tracking idea, including PHC Puck, Bertini, Julia, and minus. They all have such a functionality, but the main bottleneck is it's limited by numbers of CPU cores. Say you have 33 cores in your CPU, and currently you want to track a system with 300 solutions, and you give 1 core per track, and you need to do this 10 times. And another idea is that we need to parallelize the inner polynomial evaluation. PHP Puck already did that on GPU and give out a quite good acceleration rate. And in our work, we do hack them all and throw everything into GPU to accelerate the running of homotopy continuation. And first, why GPU? The answer, I think, is pretty straightforward. It's powerful. It has a highly parallelized structure, and it's quite portable. Recently, we have Jetson that can be installed on any kinds of drones or self-driving cars. In the multi-view geometry community, GPU is already widely used nearly everywhere, from classic visual odometry to bundle adjustment to, no doubt, the learning framework. So how are we going to parallelize them all? The first bottleneck of HC is we have numbers of solutions, and all these tracks, we need to track them independently. And within each homotopy path, following Tim's great talk, we have this prediction and this correction step. In the prediction step, we will solve a linear system. And in the correction step, and in all these two steps, we need to evaluate the Jacobians and the homotopy function themselves. All these computations takes 80 to 90% of the computation time. So in our framework, what we did is we have a nested structure. We parallelize in different levels. For each track, we track them parallelizely. And within each track, we have faster linear system solving routine, which is what GPU is quite good at. And also we have some tricks in doing evaluations of all these complicated polynomials and Jacobians. And our GPU tricks will be introduced in these three parts. Let's first see the most outer part, the parallelization of solution tracking. So here is the structure, a conceptual structure of a GPU. And the parallelization of a GPU is organized in terms of thread blocks. We can have one CUDA thread, it can be run on one CUDA core, and we have this unit called the thread block. Within a thread block, each thread can run the same instruction, and they can run quite in a parallelized way. And each thread block composed of numbers of threads running in groups of 32. This group, we call it a warp. Or in the GPU computing community, they call it a warp. So how to parallelize it? We need to assign one track to several threads for two reasons. One is that we need all these threads to do some lower level parallelization, and we need to put everything into one thread block because they can access to a set of really fast memories. We can see the memory structures over there. A thread block can access to their registers and L1 cache. They are 100 times faster than L2 cache and global memory. And for this, we cannot assign quite a lot because GPU has some internal mechanism to do some thread synchronization. And given each warp is the smallest unit that GPU will manipulate, that it will minimize the thread synchronization time. If my memory is correct, the thread synchronization within one warp is 2 CPU ticks. So as a balance, we need to assign a bunch of threads, and it cannot be a lot. Our trick is to assign one track per warp. And going to the inner part of each track, the first problem we met is we are going to solve a linear system. There are a bunch of very quick linear system solver in GPU. We have the original cuBLAS, and we have Magma. And luckily, we have collaborated with the developers of Magma library. They already have this high-speed linear system solving protocol for small matrix, meaning that if you have a really small dimensional linear system, it can solve really fast. If you compare, if you look at the chart on the right, the cuBLAS and sorry. Yeah, they have this trick. That chart is for solving. Oh, make my small slower than Kublas, and we use this fused kernel trick that one kernel can be treated as one function in GPU, and if you if your functionality are implemented in different kernels, every time you start one kernel, you need to have some overhead time. Your GPU needs to prepare for memory space for running all these kernels, and by fused all these linear system solving kernels, we can remove all this overhead time and we can reach a really fast linear system solving time on the it's shown on the right hand side on that chart. Another trick we use in the fine level parallelization is we also parallelize the Jacobian and the homotopy evaluation. Basically, the quantity we need to compute is the homotopy h and the derivative of h to x and derivative of h to the time t, the tracking step. So the trick we are using is we found that if we are doing the parameter homotopy, for example, showing like that, which is also shown in Tim's slides, and we have this example system with 5 parameters. The evaluation of each parameter of the homotopy at each step, we need to compute the coefficients of all these parameters. This computation can be rewritten into a matrix multiplication. And on the right hand side is the coefficient of current homotopy, and this matrix is the parameter of starting system and the target system. This PT is the parameter of the target system, and this PS is the parameter of the start of the start system times this T vector. And we can observe that this matrix itself is a constant in runtime, such that we can recompute this and then save this in the fastest memory in GPU that we can reuse it every time. We don't need to recompute the parameter homotopy like on the top equation. So this trick will accelerate the whole path tracking quite a lot. Yeah. With all these three, and the similar idea can apply to the computation of the Jacobians. And given using all these 3 different tricks, we can accelerate the runtime of homotopy continuation further. For all these problems, we can compare these 2 roles. We have CPU implementation of homotopy continuation, and we have GPU implementation of homotopy continuation. We can observe that some problems is even faster than the elimination template. Thanks to all these tricks. And here is the end of my talk. Here's the takeaway messages. There are GPU. Oh, sorry.
Thanks. So how does it scale with respect to the CUDA core? So it has linear scaling, or does it have some other bottlenecks in the initialization that make it, okay, we cannot go further than this, even if the next generation NVIDIA GPU comes out with twice the number of CUDA cores with respect to the scaling. I mean, it's really interesting how it scales as GPUs become more and more powerful. Do you have an idea how well?
That's a good question. Here, what I can see, or from this chart, we can observe that given the with the increasing of the scale of the problems, the accelerate factor becomes slower and slower, and we expect the next generation of GPUs can give us more more acceleration, or we can use more cores or more threads on each track. Yeah.
In the course of this work that we did, these are with a couple of experts from University of Tennessee. Now, one of them was not NVIDIA. We saw 3 generations of GPUs. And in each case, each generation gave us a big boost. So for example, from V100 Tesla to H100, we went from 80 streaming multiprocessors to 120, that just 50% faster just on that account. And as the number of cores increase and everything else, it just gives us more. We max out on their effort. It's not like we're leaving some power on charter. So we're bursting at the seams. So the more they give us, the faster those processes become. We're still not there to say, oh, it doesn't matter if they go twice as fast. We're still gonna be at the same. It's not. It's not. We still have, the HC has so many computational elements, and we really max out. We don't leave any computational power on charters.
The bottlenecks are minimized so that you can really.
Yeah,
exploit
I mean,
the
when you say how much more of GPU can I use, we can. So at least for a while, we welcome new generations of GPUs because they just drop those numbers down. I mean, just think of it now with, I think these are the V100 numbers, right?
This is the V100 numbers, yeah.
So yeah, these numbers are lower now for H100. And so you can see with the trifocal pulse estimation, 150 milliseconds, that's 7 per second. So you throw that into RANSAC now, start making sense.
Sure.
To be able to do this.
Makes a lot of work.
Yeah. Yep, that's my talk, and here is our publications related to the GPU implementation, and welcome to try our GPU HC solver. So. I'll give back to Rick, yes.
Yeah, I can connect to
By the way, the QR code takes you there.
Oh,
I have to fix that.
I'll fix that. Can connect this, even use your own.
Can you do it in this laptop?
Just to show some code, right?
Yeah, so.
Can you go back to that website? Yeah. I need to read.
How do I get in there?
Just type in the URL.
Yeah, I have
Yeah.
somewhere.
Yeah, you should have in the history, I guess.
This one?
Yes, yes. 23,735. You have an extra 3 over there. Yes.
Go.
You should log in on the side.
Let's get this one going. Well, what's happening? Yeah, tutorial.
It was logged in and then suddenly didn't logged
So-
out.
so
It
what-
was logged in, so Zoom logged out.
This is pretty,
It's kind of confusing.
it's pretty
So
confusing.
It's finicky.
It's pretty confusing.
Okay, make sure you're not muted.
I can see you are in there. Yes,
We're good?
I think so.
Recording in progress.
Yes.
No, that's not it. That's not it.
What?
That's not it.
That's not it.
No. That's just the generic,
It's not a generic.
It's not.
it's okay, we're good?
Yeah.
Xiaohong should be there. I can see. Like I'm in this meeting.
That,
and
that's what I'm saying, it's not that.
Can I share with you the? Can I send you the link? Something. This doesn't work.
Okay, just present it, don't worry about it.
Okay.
It's not nice to keep everyone waiting.
Yeah. Sorry. This city system. I don't know what happened there.
That's the link.
Yeah. Okay. You have a run. Yeah. Yeah. That's the one. Yeah. That's right. You have 3. Yeah.
That was right.
Okay. Cool.
Okay, hello, hi, okay.
First. Okay.
Okay. All right, so now that we know and have a good intuition on how it works and what we can do to make it fast, let's talk about building your own fast solver, right? How can you build so you have a new problem and you want to build a fast solver, not just run a generic slow homotopy continuation. So we have an approach. It's not so simple, but it's the right way to do it, I think. Right, so and we're improving it, so it's just not going through. Okay, so we're talking about Minus, the fast continuation solver framework that I wrote, so that the numerical method is always just the same function. I don't repeat the function, so it's just the same core tracker, and we use the same for all of the problems. Of course, you could also specialize that tracker to your problem to use your predictor, that custom predictor. That's not what we do at the moment. So we first, so the approach that we have to build, how did we build these solvers, these fast solvers? So that's how it works. You have, like in the picture in the bottom, you have first build a generic prototype, and we're going to use Macaulay 2 just because that's what generated the fastest and most stable solvers. And also Macaulay 2 worked because it happens that the tracker that it had, in the end, it had the same kind of design goals that we want for computer vision, which is speed. The other packages try to make all sorts of things, and speed is really not the main point. So, so first we have Macaulay, which is a scripting language. We build a prototype of that scripting language. And that's the basic prototype. Basically, we insert your equations, and we have it all set up for you. Just put your equations, and it's gonna solve it in the scripting language. And the scripting language uses C++ as a backend. But C++ that it uses is generic. But the advantage is code matched to our fast solver, so that you can experiment with the parameters. It's gonna be code matched to you use the same for the fast solver, right? So then once you build the basic prototype, you add some pro features, right? So your goal is to get here to the optimized solver. So you start get the generic prototype, and then you start making it faster, faster, and faster until it reaches the fastest that we have currently. So so we have basically just documented, and so how would you do this? And once you use the basic prototype, we have all the basically for each type of things that you could do, we have recommendations. So we basically divide into noob features and pro features, right? So the noob features are like standard things that you do, slow, blah, blah, blah. And then we have all these pro features that you can add to start making it faster, but you have to add kind of designing it for your problem sometimes, right? But it's very well structured. So then it worked, once it works for Macaulay, then you build a fast C++ solver step by step. So basically, we're gonna talk about the design of a fast template system. What's the idea? So that we have in mind is you can basically all homotopy continuation algorithms that you want, they're all templated, the whole process, so that you just know where to plug and play. And we're also gonna show how to design a fast executable. What I mean by fast executable is that all the input, let's say the input point correspondences or input data, it's in memory, and it's just like precisely well coded C++, so that everything is in memory. And then usually the last part of the process is just have a benchmark to test speed and robustness. So you have to test both. Right, so first let's talk about the Macaulay prototype. So Macaulay is a powerful modern scripting language. It has some roots with Mathematica as well, but it focuses on symbolic computation, even though it does have numerical algorithms like homotopy continuation. And the homotopy continuation, one of the participators is Tim. So it's the way it does is generic C++, like I said, it's code matched. And that was the origin of the fastest, most reliable solver for trifocal problems that were unsolvable before. So that's why we still advocate for Macaulay, right? And so I think one of the why they have to advocate so much for Macaulay, because it's a little bit complicated syntax, I think, for most people. But it's like when you work in Mathematica, you know, you're working with one of the best, and you have to learn the syntax. How about the optimal the C++ solver? We have a templating system that helps you build and debug your fast solver. So it allows you to test different formulations for the same problem. So you have basically a problem, you can have variations of formulations and implementations, and all of that doesn't become repeated code, and also it leverages the fact that the core algorithm is just predictor corrector for all of these problems. And if I really make a new, let's say an assembly language optimization in the predictor corrector, all of the problems are going to benefit from it, right? So this was one of an intense semester program at ISERM where we tried to solve these hard problems. So when there was a Bertini and Macaulay team trying to make it work for this trifocal problem, and the solver with Macaulay ended up being the only one that worked. So the first solver in the world for that problem was the one with Macaulay, and it took 60 seconds per solve. So you gave like point correspondences in 3 views, 1 minute, it had the solution for it. And then when we started all this process of optimizing it as much as we could, it went to like 120 faster. So that's what the point we are at. I think we want to reach 10 times faster for real time. So still a lot of room.
Single core, right?
That's
Or
4
theory.
cores using 4 threads.
4 threads.
It's kind of cheating, right? But that's what the user sees. So, but both were using 4 thread, right? So, so the optimized solver, it's that's the reference right there. Right. So the main idea is the progressive specialization. So the key to good numerical algorithms is, like I said, the knowledge to specialize the algorithms and get inside the black box. So HC is really too generic. So the start system that you have can change the solution. Even after you do the predictor, the starting point for Newton is also sensitive. Is also something that changes the speed. The evaluator is generic. Everything is generic, right? So of course it's optimized up to some point, but there's a lot of room to do that. So I do that. Had this analogy with pre-training in deep learning. So basically, you can think about the homotopy class of algorithms to be the current ones. They're kind of like pre-trained or pre-adjusted to this generic data set of all problems that people run for all fields. So all these data sets is very imbalanced towards offline problems, not for real time. So real-time scenarios are really underrepresented in this class. So the key is to fine-tune the HC model to your problem using deep learning lingo. So the first step here is, so we have, so the first step to talk about is that we're going to have 2 model problems for this. And by the way, this is going to be, afterwards, we're going to build like a resource center for the key references about predictors, correctors, and also how yeah. Right, so then we're gonna publish this tutorial so that you can actually see this happening, and but basically we're gonna have two toy problems, not two actual cases, right? The second one is a toy problem. So the first is the Chicago trifocal problem, which was the one that led to this research. That was first solved by this type of algorithm for inside minus 400 milliseconds in that case. So it's basically give it here you have some curves drawn in there, but basically you give 3 sift features in 3 views, and it computes the cameras. It's going to ignore one of the orientations. It just needs 2 orientations, right? So then it computes that. The problem has an algebraic degree of nonlinearity 312. You can think of it as, in the end, giving a polynomial in one variable that has 312 intersections with the x-axis. And that's one of the problems. That problem is really well implemented. So if you're going to build anything, base yourself off of this one. So we have this code for the problem. So Chicago was just a phone area code 312. That's why it's called Chicago, but you can give it any number, any name. And then you have this next number, which is like the size of the system or number of variables. So this formulation is 14 by 14. So A is because even if it's 14 by 14, you can use quaternions, you can use other stuff. And each of these is going to give you different equations. So you can have 14 by 14. If you eliminate differently, you're going to have different formulations. So that makes a huge difference also in runtime. So the templating system that we have accounts for that. So you have the problem, the variance. So the next one is the line circle 2A, which was also what Tim was the one behind Tim's animation. So what we have is just like a system of 3 equations and 2 unknowns. There's an A here actually. There's an A here is missing. So it's like A, B, C, D, E, and F. So it's just like coefficients, but there's a shared coefficients between x squared and y squared. Just to illustrate the fact that what are parameters? Why we're talking about parameterized systems? Because usually homotopy parameterized systems are the ones that actually perform well. The other types of it just tracks the minimum number of solutions that you want. But so the parameters, that's what it means. That you can have some coefficients, could be functions of something which reduce the dimensionality. So then this is the other one. So basically, you want to learn the basics. Just look at the solver for this problem, and then you can look at the animations to see how monotopy works. This is also 2 by 2, right? It's not 14 by 2. So let's see how it be a hands-on process. And I'm gonna outline it here and just show some things for you, but we're gonna have it up. Also, it's a project that we have to automate the process. So you have a problem, it creates a fast solver. But it could be automated to directly give you the fast solver. But even if it does that, you're gonna want to try different, like even if it's hardware level optimization. So it's important we can automate it to make it more convenient, but this is actually the like a distilled, the best way to do it that we have currently. So then first thing you clone minus, right? This is the address. And then the scripts that we are organizing, it's in minus/tutorial. So they're going to find both the Macaulay prototype, the noob prototype. You're going to find the Macaulay Pro prototype. And then you're going to move to C++ from there. Right, so first thing you start with, you type your equations, then you're gonna run the start script. Basically, start script, what it's gonna do, it's gonna get your equations, let's say that two equations you know. It's gonna generate the solutions for you, but it's gonna generate the start solutions for you. So that start solutions currently is also done generically. You could obviously optimize that using machine learning or your own algorithm, but that start script is gonna output, somehow it's gonna find a solution in a very slow way to your system. But that's slow way, you can think of it as training a neural net. It's like you do it once and then afterwards you never do it again, right? So start is like training the model, and then end is when you have a new problem, you want to solve it fast. So the start script runs slow and end runs fast.
And if I can add, just for the start part, you may need to implement your own fabrication routine depending on the problem. That actually relates to a question I got earlier. So, like in these pro scenarios, as opposed to the noob ones.
Yeah, so it might have, the problem is like, let's say, for example, it requires 3 points in 3 views, but maybe the equations are written in terms of the lines connecting the points. So then but the framework, there's a specific place you have to follow to actually make it, that you can write it there, what's the specific ones for your problem. So that way you have many executables and they all work the same way throughout, and always using in-memory and all the optimizations and all of them. So then running, how would you run these scripts? So these equations start and end, they are Macaulay scripts. So basically you just install Macaulay, and then you call M2, and then you just type load, and then the script could be equations, could be basically load start, and then it's going to write the file with the start functions, and then you just load end, and then each time, and then load end, it's going to do a fast solve. But that fast solve is still like the 60 seconds in case of the focal. You can think about that. Think of that. So so this is the generic prototype. I can show you how it looks. Just real quick. So you can always go to our website later on. We're going to update it with when everything is running smoothly, because there's some updates in Eigen as well that we're working on. They're pretty good actually. So yeah, so right, let's just go to the overview and then I'll show you some. So what's interesting here, I think, is the start script. So you have your equations, you type them. The start script is going to get those equations, going to do a low solve with some type of default algorithm. And then it's going to write to a file for the C++. It's going to write these functions to a file. So what is going to write to a file? The start solutions, and it's going to write the evaluator for all the decodings and the function itself, the age and the decodings. And the evaluator is written in a straight line program. So what you're going to see is what's in the gray box in the files. So it's going to output the like hxh.cxx and hxt.cxx. So if hx is like partial of x, right? So each of these files, they're going to have the functions already as optimized as Tim and Anton, which are the authors of the Macaulay part, they could do. It's a pretty good job, but they said there's room to improvement. So and really, I think this is the main part that needs to be optimized, because the evaluators take more than half the time. The others partial pivoting. So so then this gray box, so you have a C++ file. You're gonna have the lines are gonna look like these gates. We call it gates, and you can see that there's X's and there's G's. G's are gates. X's is just for curiosity. X's are data. So then what happens is that those lines in the gray box, they're actually these DAG that from the black parts, which are your data and parameters, it computes all these, each gate is basically, then it's just a way of computing, it's just a fancy Horner's rules for a multivariate polynomial in a way. But it's done in, I think the way they do it, I haven't seen other software, so it's pretty, this is the key for speed already. Right, so then so the evaluators, I mean, actually could look something a lot bigger than like that, so it's a DAG. In the end, you compute this value, depends on all of these guys, like that. I just showed so for curiosity, just to have a visual representation. And then, how do we start working on it? So I'll just give you an idea of the files. I'm not gonna take too much of your time. Just it's on my laptop. So for those interested, I can switch, but we're gonna put it up.
If you want 2 minutes, I will chop my computer with my mouse. Don't worry. Just 2
You wanna-
minutes though.
Can show it, I guess.
Yep.
You have time.
It's just we have a monitor here. But we really gonna make it organized. But it's in the end, like, okay, but all this trouble to make it run fast, and I want this random algorithm to make it run fast and whatever. That's not the point. I mean, the point is, if you want to make it fast, you have to go like gamer level. So you have to like really, we tried all sorts of tricks. We tried all sorts of techniques to make this happen. So I think but the steps, if you follow the way we do it, you can actually go there and really, because if you make the solver once in your life, it runs really fast, you put in the cell phone, that's it, you don't need to write it again, right? So is there? No worry, I'm not telling you soon.
Okay.
Yeah. So
That's what 312 solutions looks like.
all right, so let's take a look here. So if we go to minus, right? So then you have tutorial. That's where you should start. These are the routines basically. So these ones, don't start. So you have here, we have to pay attention here is the equation. So what we basically, you can have multiple problems here. So we always use that tag, that's probably one circle for having the equations here. For the negative problems, we have the start. And then inside these scripts, there's documented what type of stroke features are going to turn on, and we can know it's a word class feature that you can turn on because to help you. So, so here's for example, let's see the equations. How do you type equations here? Here, you don't have to memorize this, but you have this template. How you just go here and type your equation, right? And you type your variables here and the parameters, right? This is it. So this is what parameters mean. What do you guys see?
Yep.
Okay. And then you can just, these are the equations. Right, so now you fill this. Now all you have to do, you don't have to do anything anymore, just run. So what are you gonna run first? Start, right? So to start, so it's organized, if you want to know what happens under the hood, what you run is just like this. So I talk to your equations, you just go M2. And then you just load, start. That's it, right? Then you say default two solutions, as we expect. These are just, and this, it even prints in the, just so you know, it also prints in the screen those gates that we talked about for the evaluators, but it's also in the file, right? Then you just go here, here's your files. So you already have the evaluators from the start, and the start equation, it's already enough to put in the C++. So C++, you're done. This is what you need to do it. But if you want to test and play with the algorithm, you can just this is all we're done for this tutorial. So so we just then you want to do the testing and see how it works. You just do load. And then you just do end. And those are your solutions. Those are past solutions, right? And then it just shows that it evaluates to 0. Right? So it just really computes. And that's it. You can just play with that. So how does it look under the hood? So it looks like, so here we just have a description of how it works, how it was organized, but they can tell you right now how it is. So basically, we organize in new and pro, right? So here, whatever is not commented is the new part, which is the simple part. So here, this is all required, right? But here there's a pro. Look, there's a pro block here. There's all these things you can set. But for the first run, is you just need this guy. So, and then these guys, these parameters that you can set, they are all in the C++ as well. So the C++ has a bit more parameters to make it fast. You can set other things in it, but it's a superset of the Macaulay one, right? So you can always play with this to start seeing how it works. You can choose the predictor. You can see the maximum number of iterations, 3, and things like that, right? So then here, oh, how do you run? So the loop doesn't randomize, it just runs it. The pro does some type of simple algorithm for make it fast. I'm just kidding. It's actually, so here's this type of algorithm that Tim did for the trifocal is the reference for us. So it's not going to work exactly like that for your problem, but at least it's documented here what's the best way how to do it. And then you can just see what type of stuff you can do with randomization. And then randomization, I think, I have one PhD student only working on that, so I think it's a really big thing that to make it faster, but it's very difficult. Anyway, so here, see, this is where it writes the C code function from Macaulay, writes the HXXT, and then we just give some hints of things that might be useful. But this is not like organized, whatever, or this might be useful, or each line here of this file is the best way, and you can trust it, like it's the best that we know, and it's well organized, and that's what it is. So then I have got the guidelines for how to read the, like Tim said, fabricate the problem, how to do the monodromy solve. This is how the loop does monodromy. And this is how the pro does it for the trifocal. And then you put target solution count, for example. You kind of like hint at the algorithm how many solutions you expect to have, and things like that. Okay, so then that's it. I mean, this was a longer talk, that's why I'm coming. And then here in the end,
It tries to set. It tries to set. Right, so that's it. So then after that is C++. So I'll just give you half a minute Okay, so C++ is inside this command part. Yeah, so inside this command part, you can see your executables are going to be called minus/something. So as if you're like doing minus and solving it, like an inverse problem, right? So minus slash, and then the name of the thing. These are your executables. So these executables, they read the input and output in memory, so it's already well designed so that you can use it in MATLAB or anything. And then the evaluators, where they go. Just so final thing to say. So if you go minus/minus, each problem are gonna have your set of specializations of let's say there's a generic minimal solver problem that has a template, all structures of templates, and then there's a specialization. So you're probably gonna have like the name of the problem, then HXH. You can see that I have some tests here that have like some alternatives, but it's gonna have like how to do the I/O for it, how to read the points and transform to system. Here, for example, I have an optimized partial pivoting for Chicago, because then I don't have to sort all get the largest one. I just have to, the magnitude is not going to lead to numerical errors, so we can make it a lot faster by tweaking the pivoting. So then there's this, so then the line circle just goes here. So you have line circle for all of these guys. And if you look inside there, there's some types of optimizations. For example, so show you the quality of what's the level of it. Here the evaluator, after you get pharmacology, you can still do this kind of stuff, which is you have to align the data. So this was aligned, the vectors are aligned, and I look at the assembler and make sure it's using the ZMM, the ZMM vector register. ZMM is the larger original one. So if you don't do it correctly, it's going to be slower. So all of these types of optimizations you can do. The LSOL is interesting. It's simple.
I think we're-
Then half a minute.
Yeah.
We're,
Okay, sorry.
quite over time.
Okay.
I'll just take 1 minute to kind of bring everything together, maybe if I could show some slides. So, what is that? Yeah, thank you. So, just 1 minute, I'll run through these very quickly. What have we done here? Hopefully acted on the promise to bring you an overview of homotopy continuation in solving polynomial systems. First presented some examples of how these polynomials come up. What's the size of these polynomial systems? What are the various requirements? This is Hongi set it up, and that how the different approaches come short for solving some of these, forcing us to homotopy continuation, which is really nice, but it has not been workable. It's just way too slow. And so a lot of, can put up this picture about this kind of predictor corrector, about how to get there, how you can see computationally, it is expensive in these lower variable systems, and then very expensive in these other ones, but at least we can do it. At least there is a way. All these other things fail when it comes to trifocal relative pose estimation. There is no solution. Homotopy continuation is the way to go, but hey, we pay dearly for it. So then the whole endeavor is how to make this technology accessible to and Ricardo presented some that I'm not going to summarize now. But then we also went to GPU, where you have streaming multiprocessors, cores, and warps, and we worked a lot about how to
parallelize this and two concepts emerge. One is if you have to run many solutions, then do them in parallel. That's the first part, the L2 part. The inner part is we have to do a lot of linear solutions. So we actually Magma, which is a library, we made Magma a whole lot faster, completely independent of any of this, because we had to. And so this led now to much faster timing on GPU, so that trifocal could now be done 7 frames a second or 7 computations a second. And we're now at the stage where we can actually throw it into a ransack loop. And so the bottom line is, don't be afraid of large polynomial systems. If you reduce them, the degree goes up, it becomes unstable. Solve it at home, but now you have to use these techniques that Ricardo talked about, these GPU, then you can tame it if it's not too big. And so important thing is we have now a homotopy continuation resource center. All the tutorial documents are there. Software links are there, references are there, Q&A, and we're probably going to submit this as an archive. So there'll be a document for you to work with and reference if you use it in your work. And so with that, dinner is waiting. So thank you. Okay. I think you're almost out of battery.
Yes, yes, that's true. You can learn Chinese. You can read Chinese.
When the battery's done, you're done.